Hello everybody. Good morning, good afternoon or good evening whenever you are listening to me. I'm Prabin Dhakal. I completed B.E studies in mechanical engineering from Kathmandu University. And today I am going to present on the research topic Uncertainty Evaluation of Efficiency Measurement in Laboratory Conditions. Before starting the presentation, I'd like to take a time to thank Turbine Testing Lab and CRHT team for providing me this wonderful opportunity to deliver this presentation. I'd like to thank Mr. Manish Adhikari, my mate, without whom it would have been impossible to complete this research. I'd also like to thank Assistant Professor Dr. Biraj Singh Thapa, Atmaram Kayastha, Prajwal Sapkota and Dadi Ram Dahal for their inspiring guidance and help for this research. I'd also like to thank Department of Mechanical Engineering and Kathmandu University. Finally, I'd like to thank all the viewers for your time, and I hope you will all enjoy the presentation in this difficult time. So I'll be starting the presentation with introduction of the topic. Then I'll be talking about the research gap and then research hypothesis. This will then lead to objectives and scope of the research. Then I'll be discussing on the methodology followed or developed. This will then tie into uncertainty evaluated in Turbine Testing Lab. And finally, I'll be discussing on the results, conclusion and references. Alright, let's start with the introduction. Uncertainty is a parameter associated with the result of a measurement that characterizes the dispersion of the values that could reasonably be attributed to the measurand. Uncertainty in a measurement is a quantitative indication of the quality of measurement results, without which they could not be compared between themselves with specified reference values or to a standard. Uncertainty evaluation is essential to guarantee metrological traceability of measurement results and to ensure that they are accurate and reliable. In addition, measurement uncertainty must be considered whenever a decision has to be taken based on measurement results, such as accept or reject or pass or fail processes. Regardless of how careful or scientific, all the measurements subject to error and uncertainty. We can never be absolutely certain that a measurement result is true or finite. Therefore, we must establish a boundary for which we are confident that the measurement result will lie between. Therefore, uncertainty of measurement does not imply doubt about the validity of a measurement. On the contrary, knowledge of the uncertainty implies increased confidence in the validity of measurement result. The ISO Guide 5168-2005 has classified uncertainties into two categories as Type A and Type B. Type A uncertainty is the evaluation of component of measurement uncertainty by a statistical analysis of measured quantity values obtained under defined measurement conditions such as in standard deviation. Type A evaluation of standard uncertainty applies to the situation when several independent observations have been made for any of the input quantities under the same conditions of measurement. Type A evaluations in uncertainty estimates using statics usually from repeated readings. On the contrary, Type B uncertainty is estimated from any other information. This could be information from past experience of the measurements, from calibration certificates, manufacturer's specifications, from calculations, from published information, and from common sense. Type B evaluation of uncertainty is those carried out by means other than the statistical analysis of series of observations or measurement. Therefore, it cannot be reduced by increasing the number of measurements if the equipment and condition of the measurements remain unchanged. It includes information such as previous data measurement, experience with or general knowledge of the behavior and properties of relevant materials and the instruments, manufacturer's specifications, and data provided in calibration and other certificates. I just talked about how all measurements have a degree of uncertainty regardless of precision and accuracy. This is caused by two factors. the limitation of measuring instrument, and the skill of the experimenter making the measurements. Few papers have been published which includes study of uncertainties around guidelines of Francis Turbine. However, the study and evaluation of uncertainties of other testing set of components has not been done yet, and no standardization in calibration procedure leads to the need of quantification of the uncertainty for valid result. This opens a vacant opportunity to study about it in detail. These are the main research gaps that motivated to perform this research. During the early stage of this research, we made the research hypothesis that the calibration will show the percentage uncertainty in each component of type B, and the experimentation will show the percentage uncertainty in each factor of type A uncertainty. The Turbine Testing Lab is intended to be constructed in IC standard. So for any result to be valid in those standards, the uncertainty percentage of TTL should be less than or equal to 0.2%. Finally, a graph showing uncertainty band was expected as shown in figure 2. The main objectives of this research are to identify the source of uncertainties and its quantification for efficiency measurement at laboratory conditions, to develop the evaluation process of uncertainties and verify for efficiency measurement at laboratory conditions, and to study the uncertainties and recommend the solution to the efficiency measurement and calibration system available at Turbine Testing Lab. Scope of this research was limited to the calibration system available at Turbine Testing Lab for 14 kW micro Francis turbine, which was used as model testing setup for this research to evaluate uncertainty band. I would like to start the methodology of the research with description of experimental setup of simplified 14 kW Francis turbine, which you can see in figure 3. The turbine was designed and fabricated by Mr. Dadi Ram Dahal as his master's thesis. The setup consisted of an electromagnetic flow meter, 2 pressure sensors, a torque transducer, and RPM sensor. The high pressure tank available at Turbine Testing Lab was used to pressurize the water, thus maintaining the desired head and flow rate. The flow was passed through an electromagnetic flow meter and through a decreasing trapezoidal casing without the guide vanes, as you can see in the figure. The inlet pressure was measured at the inlet of the turbine by pressure sensor, while torque was measured with the help of torque transducer. The RPM of the shaft was measured using the same torque transducer. The outlet pressure was measured at the outlet of the turbine, that is at the draft tube. The test was performed for different scenarios such as variable RPM and flow rate. The design parameters of the simplified 14 kW Francis turbine are shown in the presentation slide, which shows flow is 100 liter per second, head is 16 meter, power is 14 kW, speed number is 0.667, rotational speed 1500 rpm. Also, we already established that the data taken from the calibration will be type B and data from 14 kW Francis turbine testing will be type A. As we all know, calibration has to be done prior to the experimentation. So type B uncertainty evaluation has to be done before type A uncertainty evaluation. So starting type B uncertainty evaluation, we have data block B, which consists of primary data received from LabVIEW program that is transmitted from torque transducer. The data transmitted from torque transducer to the LabVIEW program is in voltage form, that is processed into noise filtration using limits. After that, parameters are calculated such as mean, standard deviation, standard error of mean, percentage random uncertainty of mean, running average, running standard deviation. After that, convergence test is done. The data acquired from data block B are then processed into reliability test performing hysteresis test. Now, the data processed from reliability test uh, are processed to calculate calibration equation and then uncertainty equation. After processing type B uncertainty evaluation, we now move forward to type A uncertainty evaluation. In type A uncertainty evaluation, quite similar to data block B, we have data block A, which consists primary data, uh, which again consists primary data from torque transducer in voltage form. Similarly, we again perform the noise filtration using limits, and after noise filtration we convert the data which are in voltage form into Newton meter form using calibration equations. Now again, parameters are calculated such as mean, standard deviation, standard error of mean, percentage uncertainty of mean, running average, and running standard deviation. Now the data from data block A are used to calculate efficiency of the turbine and type A uncertainty of efficiency. Now we have two percentage uncertainty. Percentage uncertainty from data block A, that is type A uncertainty, and from data block B, that is type B uncertainty. We combine the percentage uncertainty of torque, pressure in and pressure out, speed and flow, and then we get the combined uncertainty of efficiency. The procedure I just discussed might be quite confusing while hearing for the first time. So I'll be discussing how we actually evaluated uncertainty in Turbine Testing Lab. In figure 4, we can see torque transducer used in TTL for this research purpose, and in figure 5 we can see torque transducer calibration setup used at Turbine Testing Lab. In figure 5 we can see 20 loads attached to the torque transducer. So these are the loads. We have fixed arm length, we have different mass numbers, and we have mass of roughly about 500 gram, and we have calculated cumulative mass and the actual torque given to the torque transducer. So when we added the mass, the torque increased, and the increased torque showed increment in the voltage value in LabVIEW program. In this way, the input we are giving is known torque and the output is voltage value. The experiment was carried out for loading, where we added the load, and unloading, where we deducted the load. So total number of samples collected for each weight was 58,000, which was 2000 samples each second. So we carried out each experiment for each load for 30 seconds. So as we can see in the slide, for fourth load, the median is calculated to be 0.2069 volt, upper limit is 0.4034 volt, and lower limit is 0.1034 volt. The upper limit and lower limit is determined using confidence level. We are now ready for noise filtration test. So for fourth loading, we have obtained this graph. where we can clearly see the voltage values represented by the yellow dots, and the black line represents average value, green line represents upper limit with confidence level 95%, and the red line represents lower limit with 95%. So this graph shows the uh, noise filtration test for the data obtained from 30 seconds. That is the data for 58,000 samples. So to zoom in the graph a little bit, here we have the noise filtration test for the first second, that is for about 2000 datas. So again we can clearly see the average value sits right there where most of the datas are centered, and the red line, that is lower limit, uh, excludes the values that are less than lower limit, and the upper limit excludes the values that are greater than the upper limit. Those values that are greater than the upper limit and lower than the lower limit are considered as noise. So after the noise filtration, the total number of samples in first second is now reduced to 1267 for the fourth loading, and for 30 seconds the total number of samples is reduced from 58,000 to 36,000 tentatively. So the calculated parameters are now standard deviation, standard error of mean, and percentage random uncertainty of mean, which you can see in the slide. Now convergence test is carried out. So for convergence test, the running average is plotted against number of samples to get a curve as shown in the graph in slide. So as we can see in this graph, the green pattern is represented as running average, the orange line is represented as average, and the blue line, vertical line, represents minimum number of samples. So as we can see here, the pattern of the running average is such that it is quite far from the average value. So as we get further in the x-axis, the curve gets slowly submerged into the average line. So minimum number of sample is the number of samples required to meet the IEC standard. That is, it is the number of sample required to get the uncertainty less than or equal to 0.2%. So for this fourth loading at number of samples 491, not only we get the uncertainty value 0.2%, but after this point all these uncertainty values are less than 0.2%. So that is quite amazing. Again, the graph shown before was for the first second, that is about 1200 number of samples, and this graph shows the convergence test for about 36,000 data, that is for 30 seconds. So again, similar to the previous graph, And the green curve shows the running average, the red shows average value, and the blue shows minimum number of samples. So for 36,000 data, we get the minimum number of samples 2788, where after this point we get the uncertainty value less than or equal to 0.2 percentage. We all know what hysteresis test is. So the medians obtained from loading experimentation are plotted in the graph, and a linear pattern is developed. Similarly, unloading medians are plotted in the graph, and linear uh, line is developed. So as we can see in the graph, the hysteresis loss uh, is quite negligible. To uh, prove this visual observation, we have the loading curve equation, that is y equals to 49.35x minus 0.2343, where we have variance r square equals to 1, and unloading curve similarly, where variance equals to 1. Now for the development of calibration equation, we have plotted the net average of the voltage and developed the linear pattern for the points. So this provides the calibration equation y equals to 49.77x minus 0.4881. Further, for the development of uncertainty in calibration equation, first of all, the uncertainty calculated in each point is plotted in the graph. Now we can see the variable uncertainty. For example, the uncertainty level at this point is greater than at this point. So the uh, the upper limit of the uncertainty and the lower limit of the uncertainty are joined so that to develop a new curve as shown in this figure. So the points are joined such that the upper limit equation is developed and the lower limit equation is developed as shown in figure. So for type A uncertainty evaluation, again we have total number of samples, and we have calculated median, upper limit, lower limit, and noise filtration test is done similarly as we did in type B uncertainty evaluation. As we discussed earlier, the data received from the torque transducer is in voltage form. That needs to be converted into Newton meter. So the data conversion is done using the calibration equation that we just developed earlier. We can see the calibration equation in the slide. So again, the parameters are calculated for the experimentation, and for constant 1000 rpm for torque, we have mean, standard deviation, standard error of mean, and percentage random uncertainty of mean calculated, which is shown in the slide. And the uncertainty calculation for type B is done using uncertainty equation or by using the interpolation. So the uncertainty is calculated as 0.078755%, which is type A uncertainty for torque. The efficiency is calculated for 1000 rpm to 59.29%. Now, as we just calculated the uh, type A uncertainty for torque, we also need to calculate the type A uncertainty for RPM, pressure in and pressure out, and flow. The type A uncertainty for torque that we just calculated is denoted by U tau A. So for the combined uncertainty, combined uh, type A uncertainty of efficiency, following the rules of uncertainty calculation, we need to add the type A uncertainty of torque, RPM, pressure, and flow, which we get 0.287188%. So after calculation of type A uncertainty and type B uncertainty, for the calculation of combined uncertainty of torque, the root sum square method is applied to calculate combined uncertainty of torque. Similarly, after calculation of combined uncertainty for torque, RPM, pressure, and flow, the combined uncertainty of efficiency is calculated by addition of percentage uncertainty of each to get 0.3387%. Now discussing the result, we have plotted the graph denoting efficiency versus RPM, where we added the error bars, which are magnified by 10 times for the visibility. So the graph shows different level of uncertainty at different points, and since we just got the efficiency for 1000 rpm to be 0.3%, which is greater than the IC standard, TTL is still trying to build up to maintain the IC standard. Evaluation of uncertainty in measurement system is very essential for every test. Since Turbine Testing Lab was initiated with the sole motive to test different turbines, standardization in calibration was necessary. The research worked on identification of sources of uncertainties and quantification for the measurement systems at laboratory conditions. It also worked in development of the evaluation process of uncertainties and verification of measurement system at laboratory conditions as per IC standards. The research was only limited to calibration of torque transducer for shaft torque measurement due to lack of equipment and resources. The efficiency of 14 kW Francis turbine at 1300 rpm is calculated in the MS by research thesis to be 66.7%, and its corresponding uncertainty is calculated to be 0.30222%. As we already discussed, the value of uncertainty required to meet IC standard is less than 0.2%. Although the result obtained is unforeseen close to IC standard, the Turbine Testing Lab needs to work on standardization more to meet the IC standards. These are the references that helped to complete this research. We thank each and every author of this research papers. Uh, Thank you so much for giving me this opportunity. Thank you for listening to this presentation. If you have any queries, you can email me at my email address. Please stay safe. Thank you.